about few of the topics that I couldn't complete in my yesterday's lecture. I had a plan to complete the topics like some of the um, optimization techniques meant for neural networks, and followed by that, I wanted to introduce you all to the topic overfitting, underfitting, generalization, and then the um, techniques that are meant to handle the overfitting problem, namely the dropout or L1, L2 regularization and all. But due to the time constraint, I couldn't complete all of them. I'll just make a small video lecture of, on all these topics that will be shared with you. You can just go through it and then you can self-learn on your own. To begin with, what you see in the slide now is the topic generalization. So there are two things that we'll be looking at, namely the memorization and then the generalization. As in when we want to train a machine learning model or an algorithm with machine learning algorithm or deep learning algorithm with the data set, with the underlying data set. So generalization, it generally speaks about the fact that a model will perform not just well with the training data, but also performs well with the unseen data or the new data. You can say that a model is a generalized model if it can performs well both with the training as well as test data. It in fact refers to the ability of trained model to perform well on new as well as unseen data that it has not been trained on. A model that generalizes well will be able to make accurate prediction on data that it has not seen before. It's a usual fact, right? If a model performs well only with the training data, that scenario is said to be the overfitting scenario. And then a model that is said to overfit with the training data will not make accurate predictions for the unseen data or test data. So that is the point. Generalization is achieved by balancing the trade-off between underfitting and overfitting. So we, when you studied machine learning in the last lecture, in the last semester, you would have been taught about what these underfitting and overfitting are. But you can easily understand the fact about the overfitting. If your model performs well only with the training data, that scenario is said to be the overfitting scenario. And the underfitting means the model will not perform either with it doesn't perform well either with the training, or I could say neither with training data nor with test data. That is what is said to be the scenario called underfitting. So these two things will play a critical role in determining the generalization feature of models. So what pictorially being illustrated in the slide at the bottom is, the test data has the one single dog of a particular breed, and the training data has, dogs of different breeds. A model can be called a generalized model or said to have generalization after training the model with all these dog images of different breeds, if it is able to appropriately classify the test set dog image as dog image, then it is a generalized model, otherwise it is a memorized model. Now, as far as the scenario that is given over here is concerned, a memorized model will be good at classifying only all those breeds of the dogs which are used for the training purpose. And for the test purpose, if something new breed is shown, the model may not be able to perform well. So overfitting are the two things. As you all know, underfitting occurs when the model is too simple and cannot capture the underlying patterns in the data. Let's say I have a machine learning algorithm which requires a lot of hyperparameters to be fine-tuned. But if I'm not going to bother about the hyperparameters, if I'm not going to use extensive number of hyperparameters with my model, let it be a linear regression model or a logistic regression model. If I won't be concerned about the learning rate, if I won't be concerned about the slope and intercept of my linear regression, then it is said to be a simpler model. A simpler model cannot capture all the essential patterns present in the data, and because of that, the model will not perform well with both the training data as well as with the test data. So the more the complexity of the model, the better the chances are for the model to learn the complex relationships, the hidden relationship, hidden insights present in the data set. Yeah, while talking about the complexity of the model, the more appropriate example that I can quote over here is, let's think about a decision tree machine learning algorithm. In a decision tree machine learning algorithm, if you keep only less number of levels, depth of the tree is very less, and the parameters that you used at various levels of the tree are said to be very simpler, having simple values, then it is a simpler model. On the other hand, if you have a decision tree with larger depth, with some complex parameters at each level, then it is said to be a complex decision tree. So a complex decision tree can understand the nook and corner of your data set, and it is able to make prediction well for both the training data as well as for the test data. So underfitting happens if the underlying model is a simpler model. In the context of deep learning, if I would like to say something about the underfitting and overfitting, in a neural network, if you keep just small number of neurons in the hidden layer, then it is a simpler network. If you keep only just less number of hidden layers, then it should be called a simpler network. So if you have such simpler networks, you cannot learn all the features present in the data set, then it may not perform well with both the training data as well as with test data. The more the number of the more the number of if larger or greater the number of hidden layers, if greater the number of neurons in each hidden layer, then the complexity of the network will get increased, and in turn it is able to understand the complex patterns present in the data set. Overfitting occurs when the model is too complex. Since I said the complexity of the model will help you to make accurate predictions for both test and training data, through that, I don't mean to say that the complexity of the model should be always high. Not like that. If your model's complexity is very high, then your model will be tending to overfit with the training data. It may not perform well with the test data. What I'm trying to say is, let us consider a deep neural network with more number of hidden layers, and in each hidden layer, if there are greater number of neurons, then your model will tend to learn not just the needed information or wanted information in the training data, but also it tends to learn the nice information which in fact we feel not necessary. So that model, you'll feel that the model is performing well with the training data, but when it sees an unseen data, the model will look for the same kind of noises to be present in the test data. But chances are very less, right? In the training data, whatever noise you have, that noise may not be available in the test data. So if the larger the complexity, more the complexity of the model will think that the noise information present in the training data is also very important. So that we should get rid of. So this is all about you. You can now see the the three plots corresponding to underfitting, overfitting, and then the balanced fitting. So the first plot shows something about the underfitting. Maybe you can call this a linear regression straight line. You cannot call this the best fit line, but then because this is the result of underfitting, the model may not be able to capture the the information present in the training data. So this you can see that here the straight line drawn over here is not on par with all the data points plotted in the Cartesian plane. On the other hand, I mean, on the right hand side, if you see the curve, this is not a straight line, but then it is a squiggly line or a curve that captures everything present in the training data, and hence it is overfitting. You can see almost it is able to align almost all the data points present in the data set by drawing this squiggly line. This is overfitting model. To this overfitting model, if you show any unseen data or test data, it may not perform well. Likewise, the center plot, it is meant for the balanced fit. This is how we want the plot to be. This is how we want the performance of our trained model to be. In this case, the model will perform well both with the training and the test data. Now, there are techniques available to reduce the effect of underfitting and overfitting. To reduce the effect of underfitting, what we can do is we can increase the model complexity, but that should be properly balanced. Because to a larger extent, if you increase the complexity of the model then will tend to overfit the data. So complexity can be reduced not to a larger extent, but to some decent extent. Increase the number of features or perform feature engineering. It is always advisable before you train your machine learning algorithm or deep learning algorithm. For deep learning algorithm and all, feature engineering is not necessary. But when you train, or when you create a machine learning model, it is always advisable to perform feature engineering that will take care of various aspects like removing the noise. If there are outliers, that will be taken care. if there is a need for doing the encoding that you can do. So all those stuff you'll do as feature engineering, that if you do properly, then the chances of model to underfit with the data will get reduced. You can also increase the duration of the training. Duration of the training is a suitable case for deep neural networks. And duration of the learning can be increased by means of extending the number of epochs. If you go for training your neural network with less number of epochs, the training duration will be very less. That you can increase by increasing the number of epochs. So here are the ways for reducing the effect of underfitting. And also for reducing the effect of overfitting, we have various ways. You can increase the training data or perform data augmentation. So data augmentation means it is feature engineering. If you feel that your data has less number of representations from each class, then you can perform data augmentation to replicate the data, to create synthetic data out of the original data. That way you can increase the size of your training data to avoid overfitting. Because in your training set, if you have very less number of instances, for instance, if you have just 100 instances present in the data set, then the model will tend to surely overfit with it. Reducing the model complexity is another way. Reducing the complexity should not be done for a larger extreme, it should be done for a smaller extreme. Because if to a larger extent, if you decrease the complexity of the model, then model would become very simple, and as a result the model will tend to underfit the data. And then early stopping during the training phase depending on the loss function. So we'll check, we'll split our data set into train, test, and validation set. Validation error we'll be checking, and accordingly, we will be performing the we'll be stopping the training of our model at the early stage. That we'll explore in the last part of this presentation. We can also go for doing some regularization technique, like we can go for doing dropouts. You can randomly skip some neurons present in the hidden layer of your neural network, so that it would be resulting in a fruitful effect. Also, you can add penalty to the loss function, so that the chances of getting overfitting will get reduced. Why overfitting happens? Overfitting is caused by noise in the training data that the neural network picks up during the training and learns it as an underlying concept of the data. So here the point that we'll have to consider very carefully is, in the training set, if there are noise information present, the noise information will be captured as essential data by the deep neural network, by the neural network, or by the deep learning algorithm. So that we'll have to be careful about, very careful about. This learned noise, however, is unique to each training set. That's what is being illustrated here. So the noise information present in the training set may not be present in the test set. So your model will be finding them differently. So when your model sees test set, the test set performance will be very poor. As soon as the model sees new data from the same problem domain, it might be medical domain or the multimedia domain or something else, but then the presence of noise is very important over there. But that does not contain this noise, the performance of the neural network gets much worse. The reason for this is that the complexity of this network is too high. So you must be very careful about considering the complexity of your network to be an essential parameter. The model with higher complexity can pick up and learn patterns in the data that are just caused by some random fluctuation or error. So noise is because of the fluctuation in your data or because of error in your data. So that should be taken care by us. The network would be able to model each data sample of the distribution one by one, while not recognizing the true function that describes the distribution. If a model is really complex, if it is relatively a complex model, then that model will tend to capture the error information or noise information that is not required for the actual data distribution that we are concerned about. So this here is the scenario that illustrates about the overfitting. So you have two curves to be explored. The left hand side curve is meant for a balanced fit or a good fit, and then the right hand side curve on the plot is meant for the high variance. So overfitting, while talking about underfitting and overfitting, it is also very necessary to look at the two things, which are bias and variance, that we'll be exploring in the next slide. So as you can see, the true function, I want my function to be like this. That is what is a true function. The true function is represented by, in both curves, it is represented by the orange colored curve. And then you have a blue colored curve, which is meant for, which shows the, the behavior of your trained model. And the data points are represented by the blue colored circles. So this is what is a balanced fit that I want. On the right hand side, what you see is a overfitting curve, because high variance happens because of overfitting. Overfit high variance in the sense your model performs well only with the training data. When it sees test data, the performance will get varied. It will vary. The performance will vary for sure. That is what is variance. So what you see is a squiggly line that the model has drawn for the training data. When it sees test data, the model will not perform well. So aware of these facts. Bias versus variance. Bias is the error that results from approximating a real-world problem with a simpler model. If you make a simpler model with less complexity, the model cannot learn anything from the training data, so hence the model will not perform well with the tested with the training data too. I'm not just thinking about the test data for this bias, because bias is very important for the training data. A model with high bias may not fit the data well, regardless of the amount of data available for the training. So a model with high bias may not fit the data well. I mean, I'm talking about the training data, regardless of the amount of data available for the training purpose. Variance is the error that results from a model being too sensitive to the training data and overfitting to noise or random fluctuations. So this variance is determined by the complexity of your model. The higher the complexity of your model, the larger the chances for you to face the variance issue. A model with high variance will fit the training data very well, but will perform poorly on new data. So these two things are said to be, contradictory with each other. If you want to take care of bias, if you want to reduce the bias, the variance will get increased. If you want to reduce the variance, the bias will get increased. So these are two opponent poles of, an object, something like that you can say. Bias variance trade-off is something, the balance that we would like to achieve between the complexity of the model is said to be the bias variance trade-off. Our goal is to find the right balance between the bias and variance. So what you see here is a plot that shows the scenario of model complexity versus error. The brown colored curve here is for the bias, and then the cyan colored curve is for the variance. Along the x-axis, what we took is the model's complexity, and along the y-axis, what we consider is the error. Now, it is quite apparent from this plot that as and when the value of the model complexity gets increased, with bias I'm talking about, if you increase the complexity of the model, I want you to focus on this brown curve. As and when the complexity is increasing, the bias is also increasing. You can just look, the bias is increasing, and hence the error is getting reduced. This is what is the point. On the other hand, if you look at the error and the model complexity with respect to the variance, we can just look at that. If the complexity of the model is less along the x-axis, I'm wanting you to look at, if the model's complexity is smaller, if it is a smaller complexity model, we can see the error is less. But as and when the complexity is increasing, the error is increasing with respect to the curve, the cyan colored curve, which is the representation for variance. So what I want is the above curve, the black colored curve, that determines the balance between the bias and variance. This is where I want the complexity of my model to be, so that the error should be an ignorable error or a decent error, I can say. So we want to achieve bias variance trade-off. Is that, and this is what is your hit bulls diagram. Bullseye diagram. So in the bullseye diagram, what you can understand is the center circle with red color is the actual output, and then you will see, that I can say as true positive. Then you will find other things like the false positive or false negative in the outer circles. You can also look at the captions given beside these circles. Low bias, low variance. If you see the model is having low bias, means the model is performing well with training data. Low variance means the model is performing well with test data too. So all the predictions that you are going to make for both training and the test set are going to be accurate. That is why all these data points are found in the innermost circle of all these circles. Now, there are other three cases that we want to look at. The model's bias is low, but then the variance is high. Model's bias is low in the sense with the training data, the model will perform well, but with the test data, the model will not perform well. So the predictions are going to be likely to be different from others, from each other, from the predictions made for training and the test set are going to be different from each other. Now, the third case to be explored here is high variance and low bias. Since the bias is high, with the training data also, the model will not make accurate predictions. But then the variance is low. Because of that, the predictions made for the test set are correct. But then the predictions are far away from the actual prediction to be made. The fourth case to be explored here is the high bias and high variance. Because of the high bias, this is going to be the nightmare. The bias is high, the model is not performing well with the training data, high variance, and thus the model is not going to perform on the test data too, on this unseen data too. So the predictions are going to be incorrect, and you will not see all these points converged within the innermost circle of all the circles. So this is the one of the best ways to illustrate the bias variance trade-off. All these four circles, what we want is the thing that is, what we want is the topmost circle from top to bottom, from left to right. The topmost circle is the circle of our desire that we want to achieve. To avoid the overfitting, underfitting, or to achieve the balance between the complexities of our model, we have several techniques that we can practice. We have regularization techniques, namely L1, L2 regularization that you have already studied as lasso ridge regression techniques meant for the linear regression optimization thing. And then you have dropouts. This is meant for dropping or deactivating randomly chosen neurons with some probabilistic values. And then early stopping means you will tend to stop the training of your model. If you feel that the model is going to overfit, the model is likely to overfit the training data, you can stop the training of your model at the early stage itself. That is what is early stopping. And we have the traditional cross validation. We will do the k-fold cross validation or the other kinds of cross validation techniques to avoid the effect of underfitting, overfitting, and to achieve the balance. We'll be exploring the first three techniques, namely the regularization, dropout, early stopping, and all. Validation is something that you know very well. So regularization refers to a set of different techniques that lower the complexity of a neural network model during training and thus prevent the overfitting. With regularization, what we can achieve is we can avoid overfitting. We'll not think about underfitting, here, but what we want to consider here is the overfitting. We can keep the overfitting under our control if we can perform regularization technique. So we have L1, L2 regularization. What you see on the left-hand side is the L1 regularization, and what you see on the right-hand side is the L2 regularization. Now here in these two plots, the green circles are representing the unseen data, and red circles are representing the training data. And then you are seeing a grayed out straight line. So that here I'm talking about the left hand side plot. So this grayed out straight line is the best fit line that you drew for the training data. Since there are very less number of instances available in the training data, the model is tending to overfit with it. And because of the overfitting, when it comes to making prediction for the test data, the model is not performing well because the best fit line is far away from the test data or the data points corresponding to the test set. To avoid this, some penalty will be added to the loss function if it is neural network. Otherwise, the penalty term will be introduced as an intercept in the linear regression equation. So this orange colored curve is the curve that will be a result of adding penalty to the intercept, this orange colored curve. Now compared to the grayed out curve that you are seeing here, this orange colored curve is much better because it is not far away from the test set instances. So this is your L1 regularization. In the context of machine learning, what we add is this lambda is going to be the regularization term. It is in fact a learnable parameter in the context of deep neural networks or deep learning. And modulus of slope, or the absolute value of the slope, is something that we'll be considering because we'll be worrying about the sign of the numbers. So the penalty that you are going to add to the L1 regularization is proportional to the absolute value of the slope. On the other hand, L2 regularization is something different. Here, we'll be seeing the penalty to be added as the regularization term into the square of the. Again, the on the right hand side, the red colored curve is the overfitting curve because we got only less number of instances in the training data. The model was overfitting the training data, and because of that, with the test data, our model will not perform well. By adding this penalty, you will get a new curve, that is the cyan colored curve. The cyan colored curve is the result of adding this penalty to the machine learning algorithm. Now this is somehow better than the curve that was originally drawn with the training set. And the point here is the penalty that you are going to add to the L2 regularization is proportional to the square of the slope that we'll be exploring in the fourth. So L2 regularization is something that we'll be considering here. During the L2 regularization, the loss function of the neural network is extended by so-called regularization term, which is called the omega. This is the capital letter omega in that you'll find in the Greek letters. So we know about loss function because in all the previous lectures we had extensive discussion on the topic loss function or cost function. Loss function is something that determines the deviation from the actual output, or I could say the difference between the distance between the actual and predicted output to something called the loss function. So that loss function will be extending that loss function by adding some penalty term into it so that model will not be overfitting the training data. The penalty term that we'll be adding for the L2 regularization is represented by big omega. Big omega of the weight W is equal to the square of the sum of the weights. So the weights are represented over here, summation I, summation j. You know very well that Wij stands for the weight associated between the link from the ith neuron in one particular layer to the jth neuron in the next layer. And we are just taking the square of that because the penalty in L2 regularization is proportional to sum of the squares of weights. So the new loss function can be represented by the following equation. L hat of W is equal to lambda by 2, which is the penalty term, sum of the squares of weights plus whatever loss function that you will be originally calculating. So what we do with L2 regularization is we are going to extend the loss function, the original loss function, by adding some penalty term. That penalty that we add here is proportional to sum of the squares of weights. This is what is your L2 regularization. What we see here in L1 regularization is L1 regularization is also about extending the loss function, but here the extension that you are going to add to the loss function is proportional to the absolute value of the sum of the weights. Earlier in the L2 regularization, it is sum of the squares of weights, but here it is the absolute value of sum of weights. So the penalty term that we are going to add to the last function here is omega of W, which is equal to absolute value of sum of the weights. Sum of the weights is represented by summation I, summation j, and Wij is the weight associated between weight associated with the connection between neuron I and the neuron j. So this is going to be my new loss function. L hat of W is equal to penalty term lambda summation I summation j absolute of sum of weights plus the original loss function L of W. So this encourages the weight to be sparse. You can have sparse weight for this. It is particularly useful when the data has many irrelevant features. Okay, it's now time to look at when I can use L1 regularization and when is the L2 regularization is suitable. L1 regularization you can use just by looking at the information present in your data set. You can go for drawing a pairwise plot. The pairwise plot will say how many features in the data set are highly correlated with each other and how many else are not related to each other. If you have more number of irrelevant features in the data set to the dependent variable, then it is better to apply the L1 regularization. If you have multicollinearity problem present in the data set, I mean to say after drawing the pairwise plot, if you can find the inference that there are large number of features which are highly correlated with each other, then you can go for applying the L2 regularization. Dropout. In a nutshell, dropout means that during training with some probability p, a neuron of the neural network gets deactivated or turned off during the training. So it randomly drops out a fraction of neurons in the network. I mean, especially neurons available in the hidden layer of your neural network will be dropped out. It is because if you keep all the neurons as is, then they'll be capturing all the unwanted information, noise present in the data set. So what we do is we'll be ignoring or will be deactivating some of the neurons randomly. That reduces the chances of overfitting. A simpler version of the neural network results in less complexity that can reduce overfitting. So that is about dropout. Uh, a lot of details about the dropout in the forthcoming practical sessions. And the last and final way of avoiding overfitting as far as the syllabus is concerned is early stopping. So we keep a set of data as a validation set, and as we go on training, we keep a record of the loss function on the validation data. As you all know, the original data set that you have will be split into training, test, and validation sets. As and when you do training, you will also have an eye on the validation set. Validation errors, you will record, you will draw a plot for that. And when you see that there is no improvement on the validation set, you will stop rather than going all the epochs. If there are 1,000 epochs you have decided to perform, but after reaching the 500th epoch, you will not find any improvement in the validation set performance, then instead of continuing with the remaining epochs, you can better stop the training. That saves your time, that allows you to come up with a newer model or a complex model. This strategy of stopping early based on the validation set performance is called early stopping. Now what you see here is a plot that shows that is in fact an error plot or accuracy plot corresponding to the validation set and training set of a particular model. You can see here the model's training set performance is indicated by training set accuracy is indicated by the blue curve. The accuracy is likely to increase as and when you go through the number of epochs, but then the orange colored zigzag line or squiggly line is for the validation set accuracy. There is no improvement in the validation set accuracy. So you cannot just depend on the training set accuracy, which will be leading to overfitting of your model. So you can also consider about the validation set accuracy. Since there is no improvement in the validation set accuracy, you can stop for the training. So here the point, the saturation point that you have reached is from 0th to 10th epoch. Around in the 8th epoch, what you found is you are finding that there is no further improvement. So after the 10th epoch, it is better to stop the training. There is no need of continuing with the training. So this is what is early stopping. You can just go through this video lecture. The material also I'm going to share right away. You can go through both of them and do your exams well. Bye.